Welcome to a new session on the massive open online course Introductory Concepts of Digital Computing offered by Swayam. In the last two sessions, we were discussing on different binary codes. During this session, let us talk about two other codes used for error detection and correction. The data transmitted over a network or the data stored on a medium may get corrupted due to some undesired phenomenon results in erroneous data. Due to data interference, noise or some spots or scratch on the disk or due to many other reasons, the stream of data gets affected. This may be flipping of data bits or losing some bits or even some bits are added. We can't avoid these, but somehow we need to get back the valid data. In order to receive or retrieve the valid data, error detection and error correction codes are introduced. It is designed by a set of one or more additional bits attached with the source data. These additional bits that help to detect and correct errors are called check bits. These are attached with the original data bits to form a valid code word. When you identify that a code word is invalid, that is error detection. Next, we need to locate the bit positions to correct it, that is error correction. There are many techniques available for error detection and correction. During this session, we are going to discuss two of them, parity code and alphanumeric code. Let us first discuss the parity method for error detection. As we know, any group of bits contain either an even number of ones or odd number of ones. Parity bit is a single bit added to a group of bits to make the number of ones always even or always odd. There are two types of parity codes, odd parity and even parity. We follow any one of them. If we use a system which operates on even parity, then the number of ones are to be made even always. Similarly, in a system of odd parity, the number of ones are to be made odd. So, by checking the number of ones, we will be able to detect whether an error has occurred or not. Check for the total number of ones. If it is even, in system that follows odd parity, then we realize that an error has occurred. So, we have to make sure that the total number of ones are even in a system that operates with even parity. The same for odd parity also. Even parity code. Even parity code contains original data bits and a parity bit with a total number of even number of ones. The value of this parity bit should be 0 if even number of ones present in the binary code. Otherwise, it should be 1 so that we can maintain the number of ones always even. Parity can be used with any number of bits. Let us see the even parity codes corresponding to 3-bit binary code. We consider even parity bit that is included to the right of LSB of binary code. In some cases, it is added to the left of the most significant bit. It depends on the system's design. See the table. Here the number of bits present in the even parity code is 4. In the first row, the actual data is 0, 0, 0. As we use even parity and this data does not contain any ones, the parity bit is set as 0. In the second row, the data bits are 0, 0, 1. It has a single one. So, we add the parity bit as 1. Then the valid code word even parity code becomes 0, 0, 1, 1. Consider the data 1, 0, 0. It has odd number of ones. We add a parity bit 1 and the even parity code becomes 1, 0, 0, 1. When you observe closely, you can see that the number of ones in this 4-bit even parity code are always 0 or 2 or 4. So, when you receive a coded data, if the number of ones are not 0 or 2 or 4, then it is sure that some error has occurred. Though you are able to detect the presence of errors, here we will not be able to locate the erroneous bit positions. The next odd parity code. Here we maintain the number of ones as odd. The value of odd parity bit should be 0 if odd number of ones present in binary code. Otherwise, it should be 1. Odd parity code contains the data bits and odd parity bit. The 4-bit odd parity code corresponding to each 3-bit binary code is shown in the table. Here, the odd parity bit is added at the end of binary code. For the binary code 000, we add an odd parity bit 1 and the parity code becomes 0001. And in the next row, the binary code is 001. There we have odd number of ones. Then we add the odd parity bit as 0 and the odd parity code becomes 0010. And it is the same procedure we use in all other rows. Here, the number of bits present in the odd parity code is 4. So, the possible odd number of ones in these codes are 1 and 3. So, when you receive a coded data, if the number of ones are not 1 or 3, then it is sure that some error has occurred. Using odd parity code, we can detect odd number of errors occur in a data bit stream. For example, we need to transmit the data 110101. It is a 7-bit data. Assume that the system follows even parity. How do you create the code word? The data word has 5 ones, so add a 1 at the end to make it an even parity code. Then the code word becomes 11011011. Assume an error occurred in the 3rd bit from left. So, it becomes 11111011. While receiving this code word, the system checks for even parity and found the code word as invalid. Why? The number of ones are odd. This indicates an error. Hope you understood the concept on parity. One more code we are discussing today is Hamming code. Hamming code is useful for both detection and correction of single error present in the received data. This code uses multiple parity bits to create a code word. Consider we have an information of m bits to be transmitted. We add k parity bits to form a code word of m plus k bits. How do you determine the value of k? There is an inequality to find the value of k. It is 2 raised to k greater than or equal to m plus k plus 1. That means, the minimum value of k for which m plus k plus 1 is true is nothing but the required number of parity bits. For example, we take the number of information bits as 4, that is m equal to 4. Then, how many parity bits are to be added? If k equal to 1, follow the inequality m plus k plus 1, then 2 raised to 1 is not greater than 4 plus 1 plus 1, that is equal to 5. So, k is not equal to 1. If k equal to 2, 2 square equal to 4, that is not greater than 4 plus 2 plus 1 equal to 7. That does not satisfy the condition. Then check if k equal to 3, 2 cube equal to 8, which is equal to 4 plus 3 plus 1, m plus k plus 1. So, the value of k is set as 3. Okay. K equal to 3 and total number of bits in the Hamming code will be m plus k bits, that is 4 plus 3, which is equal to 7 bits. The number of actual data bits are 4. 3 are parity bits. Where do we position these parity bits and data bits? That is the next question. The parity bits are inserted in the positions of powers of 2. 2 raised to 0, 2 raised to 1, 2 square, 2 cube, 2 raised to 4 positions, etc. What I have discussed now was just for 4 bits. Now, I will generalize it to n bits. Let the Hamming code is Bn plus k, Bn plus k minus 1, etc., B3, B2, B1, and parity bits are Pk, Pk minus 1, etc., P1. Then we can place the k parity bits in the powers of 2 positions. The remaining bit positions are occupied by the n information bits. Depends on the system design, either even parity or odd parity can be used while forming a Hamming code. The same parity technique must be used for error detection and correction. For example, if m equal to 4 and data to be coded is 1101, as we said, we have to generate m plus k, that is 7 bit Hamming code, and the powers of 2 positions are for parity bits. First, mark the powers of 2 positions, the shaded regions, and the remaining positions are for the data bit 1101. Hope it is clear to you. If m equal to 7, then k will be 4, 2 raised to 4 is greater than 7 plus 4 plus 1. Then the parity bit positions and data bit positions will be as given in the figure. The next task is to find the value for these parity bits. The bit positions in Hamming code is determined in such a way that each of the data bit is included in a particular set of parity bits. All bit positions whose binary representation having a 1 in its LSB is covered by P1. So, P1 represents the bits of positions 1, 3, 5, 7, 9, 11, etc. So, to find the value of P1, count the number of ones present in those bit positions covered by P1. Assume that we follow even parity code, then the total number of ones including the parity bit must be even. So, the count of ones in the positions 1, 3, 5, 7, etc. are even, assign 0 to P1, otherwise assign 1 to P1 to make it an even parity code. Parity bits can be obtained by calculating modulo sum of these bits. Counting the ones gives the same result, that is all. Similarly, all bit positions whose binary representation having a 1 in its second position from LSB is covered by P2. So, P2 represents the bits of positions 2, 3, 6, 7, 10, 11, etc. So, to find the value of P2, what should we do? Count the number of ones present in the bit positions covered by P2. Then, if the total number of ones including the parity bit is even, assign 0, otherwise 1 to P2. In the same way, the bit positions having a 1 in the third position of its binary representation from LSB is covered by P3. So, P3 represents the bit positions 4 to 7, 12 to 15, 20 to 23, etc. As we did in the previous cases, here also we can assign the parity bit. I hope that you understood the procedure of assigning values to parity bits and generate a Hamming code. Let us do one example. Find the Hamming code for binary code 1000. Assume even parity code. Here, the number of bits in the given binary code is m equal to 4. We have already discussed that when m equal to 4, k will be 3. We must place the parity bits and bits of binary code in the right positions. The parity bits P1, P2, P3 are at 1, 2, 4 positions respectively. The data bits are placed in 3, 5, 6, 7 positions. To obtain P1, count number of ones in the positions 1, 3, 5, 7. 1 is the position of P1, you may leave it now. From the remaining positions, the number of ones is 1. It is an odd value and we follow even parity. So, what should be the value for P1? it must be 1. Then only bits 1, 3, 5, 7 can maintain even parity. Done. Next, find value of P2. Here we count values of positions 2, 3, 6, 7. Again 2 is the position of P2. We will write this later. From the remaining positions, the number of ones is 1. Again it is an odd value, so write 1 for P2. To obtain P3, consider bit positions 5, 6, 7, all are 0, so P3 equal to 0. Now, the Hamming code for 1000 is generated as 1110000. This is the data to be transmitted over the network. All what we have done here happens at the source. What happens at the destination while receiving this data? It has to check for errors. Here we reverse the process. At the receiver side, we have a 7-bit data 1110000. Here the bits of powers of 2 positions are called as check bits at the receiver side, C1, C2, C3, etc. These check bits help us to detect and correct the errors. C1 is the bit at 2 raised to 0 position, C2 at 2 raised to 1, C3 at 2 square positions. We have to ensure whether all check bits are valid or not. To check the value of C1, we consider the bit positions 1, 3, 5, 7 as we did in the case of P1 and check for even parity. If it does not follow, that means C1 is invalid. Again check for C2. Consider bit positions 2, 3, 6, 7. Check whether it is valid or not. Find the values of all other check bits in the same manner. There may be one or more check bits which are invalid. That just indicates the presence of error. Then next we have to identify the location of the bit where error occurred. We have already calculated the values of check bits. Write down these bits in sequence where C1 starts from the right. So, the bits are arranged as C3, C2, C1 order. This will give us a 3-bit binary value. If this value is 0, there is no error. Otherwise, the value indicates the location of the error. If it is 0, 1, 0 means that the error occurred in the position 2. Straight away we can correct the bit value by complementing it and get the corrected data. After removing the parity bits from the corrected data, we get the original bit sequence. Consider the Hamming code 1110000. I just flip the 4th bit, it becomes 11110000, the error data. While receiving this data, we calculate the check bits. They are C1 equal to 0 by considering the bits 1, 3, 5, 7. Then C2 equal to 0 and C3 equal to 1. Write all CIs in the reverse order as C3, C2, C1. We get 100, which is 4 in decimal. This indicates that there is an error at the 4th position. The received Hamming code is 1111000. The 4th bit here is 1, that is the error bit. So, complement it. We obtain the transmitted value 1110000. Then remove all check bits. We get 1000, the original data. By this session, we finished the discussions on binary codes. Here I conclude the discussion of error detection and correction codes too. Let me summarize the topics we discussed. By this session, we finished the discussions on binary codes. Let me summarize. Binary information can be transmitted from one location to another through a communication medium. Any external interference may be introduced to the data either in the communication medium or in the storage medium. This is to be detected and corrected for the reliable data transmission. This module was planned for discussing the error detection and correction mechanisms. just by seeing the data bits, we won't be able to say whether error has occurred or not. So, we add some extra bits known as check bits to the original data to form a code word. If an invalid code word is encountered, we realize that error occurred. We have discussed two codes, parity and Hamming code, where parity is used only for error detection. Hamming code helps in detecting and correcting single bit errors. Thank you for watching. See you in the next session. Bye.